Hello, hello, hello. It's Brennan here. And today I wanted to walk through a practice project I've been working on for a course that I'm taking from Duke University. So the past 6 weeks, I've been learning all about machine learning and AI, the different types of models, the challenges and strategies and how to overcome them, different algorithms to kind of think about, and common just ML tasks and use cases. It's been really interesting, especially coming from the user experience field, where we think about problems in a very different way. But now knowing more about AI and machine learning, I can think about how can we use the UX to start enabling more efficient model training, and how can we use parts of our users' behaviors and interactions to then help kind of feed into the inputs of any sort of model training and things like that. So it's been really interesting. And so this is my capstone project for this course, which is the final project. And I'm going to walk you through that today. So the project is to predict the energy output for a power plant, and the hourly energy output for a power plant. And we're going to work, and I'm going to talk through the data that we'll be assessing and evaluating. So my personal objective for this was really just to apply my learnings through firsthand experience, through a project-based format, to continue to solidify my understandings of ML and the workflows involved, and then really just get something up and running and start predicting, right? That's why we use AI and ML, is to kind of look ahead and predict intelligently. The project objective was really to develop a model to predict the energy output of the power plant, evaluate the performance of the model, and deploy the model for testing. So back to kind of our problem. So why is this problem worth solving? So if you think about a power plant, accurately predicting how much energy a power plant can generate is crucial when planning out the supply and demand a city or part of a neighborhood might need. If done incorrectly, an inaccurate prediction could result in the rise per unit costs of electric power, could result in power outages and other unplanned difficulties. So for this project, they gave us students a data set, which was quite simple and straightforward and pretty clean. It's coming from the UCI machine learning repository. And the data was collected over 6 years with over 9,568 data points. The AT here is the ambient temperature for a particular power plant. The V is the exhaust vacuum. The AP is the ambient pressure. The RH is the relative humidity. And the PE is the net hourly electrical energy output. This is actually the target feature we'll be looking to predict here. So for tooling, I chose to go down the path of a very low-code machine learning platform called Vertex AI. It made it much easier for me to kind of just step into it with the data and to start playing around with it, evaluating it, and working with different models and algorithms, and then deploying quickly. The workflow for this project was to just explore the data, to develop a model, evaluate the model performance, and then select the best one based off the performance. So great. So first I took the CSV and uploaded it into Vertex AI for just further exploration. And with over 9,000 rows and 5 numerical features, and also no missing data, the cleaning was basically non-existent and quite straightforward. So super lucky there. As I've heard, cleaning is basically 60% of the data scientist's job, so I didn't have to really endure the pain points and the struggles there. But after reviewing the data and getting familiar with it, I went ahead and started kind of configuring the model. And so since the data consists of mostly of all numerical values, and since we're kind of looking to make a prediction, I knew some sort of regression model made the most sense. And for this project, I chose linear regression for kind of the reasons, for the following reasons. The first was linear regression is a simple model to configure and kind of a great for a first stab. And it's a little more interpretable and easier to understand when it comes to the relationship between the inputs and the outputs. and also can be surprisingly effective. And so I figured, don't overcomplicate things, Brennan, and let's start with linear regression. Let's get something up and running. See how that does. So I went into Vertex and selected the model and started configuring the training options. Once I had my training set up, it was time to select the target outputs that I wanted to predict. And since we said before, the net hourly electrical energy output is what we're trying to predict, I chose PE as our target column. Also, the really nice thing about Vertex is that the training and test data split was done for me. So they automatically took the data and they split it off into kind of making sure that we're not dirtying our cross training between, or we're not testing our model with our training data and vice versa. So that was really nice, a nice feature. So I did this and then kind of put this model together and ran it a few times, and I learned that the ambient temperature was one of the most important features to kind of keep your eye on. And after the discovery of that, I saw the correlation between the ambient temperature and our target output, which was PE, the net hourly electrical energy output. So with that, I went about basically just weighting AT, ambient temperature, more than the other features. And in order to measure the model errors appropriately with an effort to kind of penalize the larger errors, I chose to go with root mean squared error as well. So as you can see here. Great. And so when I went about evaluating the model and the error metrics, you could see, I won't go through all these, but for the root mean squared error, which is the root of a squared differences between observed and predicted values. Generally, a lower value indicates a higher quality model, where 0 means the model made no errors, which obviously we don't want. It'd be probably overfitted. And interpreting root mean squared error depends on the range of values in the series, and it's more responsive to kind of large errors than like a mean absolute error. I won't pretend to know much more about that than what I just described, but kind of seeing that we're at a 4.841 kind of reassured me that we're not, it's not terribly high, but it's also not too low. And so I felt pretty good about kind of moving forward with this version, this model that we created. So I went ahead and began building the endpoint for the model deployment. Vertex, again, makes this super easy. After I named the endpoint, I entered the model settings like the traffic split, compute nodes, and machine type, and just simply hit deploy. Very simple. So about 10 minutes later, the model was ready to go for a spin, right? And as we'll walk through here, we have this is our kind of training data, the data that came with the CSV. Of 41, and then the exhaust, and then the ambient pressure and the humidity, and then the target output. And taking some of the test data, I started to input that into our model to start predicting. And so I entered in 62, 1020.04. And then for the relative humidity, 59, and we were able to predict, kind of get our predictions based off of those inputs, those features. And what you'll see here is we have 445.34, but with the test data, the actual data in actuality was actually 444.37. So really not too far off. And as you can see up here, showing a 95 prediction interval, which is pretty interesting to see how close they are. Again, no idea. We might be overfitted here, but for someone new to kind of building models, this is really exciting to see that we're starting to predict and make predictions here with the model that we created. So Uh, so like I said, this lands our model at about 95% prediction interval with a root mean squared error of 4.841. Uh, Again, my gut is kind of telling me that maybe this is too good to be true and it's probably overfitted. But nonetheless, I've made my first prediction, and that was kind of the goal for this entire project here. So to wrap up with a model that is most likely overfitted, my next step would be to try different regression algorithms like decision tree regression or random forest regression, for example, until we've evaluated all of our options to kind of find the one that returned the best performance. However, since I only had kind of a weekend to put this all together, the model training and the deployment piece of it, I kind of, and since I also hit my personal and project goals, I was ready to kind of wrap this up and move on with it. But I wanted to talk about a few things that I learned from putting together this model. The first was really just getting that first-hand experience developing and going through the workflow, just getting exposure, becoming empathetic with, at a very high level, some of the things that our AI researchers and data scientists are working with and working through on a daily basis. Granted, in a much more complicated problem with much more dirtier data to work through. Totally can't relate to that. But the second was really just trying to be able to get this experience under my belt, so I could think about it and talk to our researchers in a collaborative way to say, all right, what can we do to make the predictions a higher accuracy, higher confidence scores? And going through the process myself, I can really think about how do we design experiences to enable that. And then the last piece was really just seeing the difference between running the model with weighted target columns or weighted features and unweighted ones, and to realize what are those key inputs that really change your predictions and outputs, which I thought was really interesting. So I hope you found this recap really. I hope you found it insightful at the very least. I hope you saw that approaching a numerical problem like this. Granted, it was very simple and straightforward with the data, but that AI and approaching it maybe even with low code situation like this, it doesn't have to be rocket science or overcomplicated to start thinking about your problems using ML or AI. So until my next course in my next AI application, I hope you enjoyed this, and until next time, see ya. Thank you.